This is Module 28, Volume of Prisms and Cylinders. First thing I have to identify is what the formal definition of volume is. The volume of a solid is the number of cubic units contained in its interior. So if you see to the right here, I have a rectangular prism. In the bottom part, I have the length here is 2 units. I have the width back here is also 2 units, and I have the thickness, or the big height, is 4 units. So if I kind of superimposed little cubic units within this, you would see that if I multiplied all these, I would get 8 times 2, which is 16. And if you counted the boxes, so I have 1, 2, 3, 4, 5, 6, 7, 8, and then I have 8 in the back as well. You add them together, that's 16 units, and we call it units cubed. So in this particular module, we're going to be finding units cubed, volume of prisms and cylinders. So, a couple postulates. The volume of a cube, we had a rectangular prism back here, very similar, only in a cube. The length, width, and the thickness in the third dimension are all the same. So the volume of a cube is going to be the side length cubed. We have a volume congruence postulate. If two polyhedra are congruent, that means that they are going to have the same volume, and you can actually prove that by the transitive property. Volume addition postulate, again, we might have more than one figure or volumes overlapping, so you have to actually figure out the non-overlapping parts, but the volume of a solid is the sum of the volumes of its non-overlapping parts, so it's the amount that it takes up in a three-dimensional space. Okay, so here's an example. Like, for example, we have a cube here to the left, we have a rectangular prism to the right, and we have a rectangular prism in the bottom here. So there's actually 3 different figures that are going on at this point to figure out the total cubic inches. So all you do here, what you could do in this particular model is you could actually just physically count the number of boxes. So like 1, 2, 3, 4, 5, 6, 7, 8 for the cube. So this would be 8. And then we have 1, 2, 3, 4, 5, 6, 7, 8 for the rectangular prism. And then we have 1, 2, 3, 4 for the other rectangular prism. So if you added those all together, you would get 20 units cubed for the actual volume. But here's the thing. You're not always going to have these actual cubes to kind of look at and to count up. So what you have to do is you have to split it up into volume parts that you understand. So for example, this would be an S cubed. So we have a 2 by 2 by 2. So that'd be 2 to the third, which gives you the 8. Here you have a width here. The bottom part here is 1, 2, 3, 4. The thickness is 1, 2, and the height is also 1. So this would be a 1 times 4 times 2, which gives you 8. And here you have a length of just 1. You have a thickness, a height of 2 units, and you have a width of 2 units as well. So this would just be 1 times 2 times 2, and that gives you your 4. So all I'm doing is I'm splitting it up into prisms that I understand, which creates the entire volume of this particular puzzle piece. Okay, so here's the theorem. The volume of a prism, of any right prism that we're going to be dealing with, or right cylinder, can be found by multiplying the area of the base times the height. So one of the things you have to identify in prisms is what your base is. So if you see to the right here, you have a pentagonal prism. Here you have a triangular prism. And here you have what looks to be either a rectangle or a square prism. So what I like to refer to this as is the big B times the big H. The big B is the area of the base, whatever that area may be. So in this case, this is a pentagon, so we'd have a pentagonal prism. That would be the area of the base. And you don't have to do it like surface area and find the area of the base twice, because we're not finding surface area, we're just finding the volume. So you'd find the area of the base, and then you multiply it times your height. So that would be your big H. And the reason I refer to it as big B and big H is because if you look at, like for example, a triangle, the area of a triangle is 1/2 your base times height. But I call it as little b times little h because this is a two-dimensional figure. Here, we're now talking about 3 dimensions. So 3 dimensions means that I'm going to be referring to this as big B, big H, and little b and little h are going to be referred to as the two-dimensional figures. Volume of a cylinder is the exact same thing. The only difference is that we now know that our base is actually a circle. So we know, again, it's the area of the base, but the area of the base in a cylinder is going to be the pi r squared formula. So that's our big B. So we'd have our big B would be our pi r squared, and our thickness, our height, our big H, is how high it is in the 3rd dimension. So honestly, the volumes of prisms, those are harder. Volumes of cylinders are usually pretty straightforward, pretty easy. Where the prisms can get a little challenging is when you have something like a pentagon, a regular pentagon, a regular hexagon, heptagon, something like that. And you'd have to use trigonometry to figure out the certain area like we did in a previous module. Okay, so I have a few things here. It says in A, find the right trapezoidal prism, the volume of this. So what you have to do is find out what your big B is times your big H. So your big B times your big H. Well, the big B in this case is a trapezoid. We know it's a trapezoid. They tell us it's a trapezoid. So that means the area of a trapezoid is 1/2 the thickness, the height that is, which is 3 in this case because that creates a perpendicular segment. And then we have the one base is 14. The other base is 6. Even though it's labeled down here, you can still transfer it up here. And that will give you the area of the big B. The big H, that's just the thickness in the 3rd dimension. So the thickness in the 3rd dimension would be the 5, what the 5 is referring to. So you can plug this into a calculator. I get 30 times 5, and that gives me 150. Now the thing that I stress as much as I possibly can is units. You need to make sure you have your units. If you don't, just think about if you're doing building materials and building something that is a right trapezoidal prism, whether it be like a play set or part of a house or something like that, you need to make sure it's cubic centimeters. Because if you put something that's just 150 down on a piece of paper and somebody has to go out and get materials, they're not going to know what you mean. So be specific. So right cylinder, again, in this case, we have our big B, which is a circle. So we have pi times the radius, which we know is 9 squared. So that's our big B. And we times that by the thickness in the 3rd dimension, which would be 6. Now, it's completely up to you. Typically, when you're doing either quizzes or tests, some teachers will specify you use either the pi button in the calculator or use 3.14. Me personally, I'm going to just keep pi in my answer just because I think it's a little more exact. But if it specifies it on a quiz or a test, or if you have questions about it, let me know. But this would be 486 pi. And that's the most exact answer that you can have. Feet cubed for volume. Okay, but if you were to use like 3.14 in your calculator, you get 1526.81 feet cubed. Unless I specify, either answer is acceptable. Okay, so in this case, I tell you the volume of the cube is 90 cubic inches, and I ask you to find the value of x. So find the values of the dimensions. So if we know the volume of a cube is s cubed, so the side length times itself 3 times, that means that x cubed would equal 90 cubic inches. How do you get rid of the 3, the exponent of 3? Well, you have to do what's called the cubed root. Cubed root. So anything to the power, you have to do the reciprocating power, which is taking it to the whatever root the exponent is. So in this case it's 3, that means it's going to be to the third root. So 90 in terms of third root, if you plug this into a calculator, you get roughly about 4.48 inches. And it's just inches because we're just finding one side of the cube. So it would not be inches cubed because we already have the cubic inches. Okay, this is a theorem called Cavalieri's principle. And basically what is evident about this, why this is useful, is because we're going to not only be talking about right prisms, we're also going to be talking about oblique prisms. But if two solids have the same height and the same cross-sectional area at every entry level, cross-sectional area, just think of it as like you're taking a rectangular for the two-dimension and going from the bottom all the way through to the top. If you have the exact same figure throughout, that means that they're going to have the same volume. So, Cavalieri's principle. And all I'm going to be doing is I'm using Cavalieri's principle to apply using oblique prisms. So in this case, it says find the volume of an oblique cylinder. Again, using Cavalieri's principle, you know that the cross-section is a circle on the base. That means that it is all the way throughout. Since it is an oblique cylinder, that means we can use the area of the big B and then times that by the big H. So again, in this case, we know that we have pi times the radius, which is 4, quantity squared, times the thickness, which in this case is 7. That's how high it is because we're dealing with a right or perpendicular segment. That always has to be the height or the thickness. Always has to be a right angle created. So if you do this, you get 16 pi times 7, which gives you 112 pi. And it's centimeters cubed. Again, if you want to use the 3.14 or the pi button, you get roughly around 351.86 centimeters cubed. Either answer is acceptable, but in some cases I might ask for something in terms of pi or something in terms of a decimal. And that's it.